Greetings. This is Nate's presentation of homework assignment 7, problem 8, where in the first part, problem A, we have the probability of the random variable x equal to k, and that's subsequently equal to e to the minus lambda raised to the lambda k over the k factorial. In this first part, we're pretty much asked to determine the expected value of the random variable x. Now, knowing that basically we have the summation from k0 to infinity of e to the minus x times lambda, it's not e to the minus x, it's e to the minus lambda, I'm sorry, times lambda to the k over the k factorial, and all of this equal to 1 with certainty. This implies, however, that the summation from k equals 0 to infinity of lambda to the k over the k factorial is equal to e to the lambda, which implies that if you take a derivative of that summation from 0 to infinity of lambda to the k over the k factorial, it will equal the derivative of e to the lambda over d lambda, which implies that the summation k equals 0 to infinity of k times lambda to the lambda minus 1 raised to the minus 1 over the k factorial is equal to e to the lambda. This, of course, implies the summation k equals 0 to infinity of k times lambda to the k over the k factorial, which is equal to the first derivative of e to the lambda, which is lambda to e to the lambda, which implies that the summation from k equals 0 to infinity of k times e to the minus lambda, lambda to the k over the k factorial is equal to lambda, which basically occurs by not manipulating, but basically multiplying the previous by e to the minus k. So it basically, I'm sorry, I said k, but it has to be e to the minus lambda to bring lambda over to this side. I mean, to bring e over to that side, which eliminates and leaves just plain lambda. Therefore, implies that the expected value of the random variable x is equal to the summation from k equals 0 to infinity of k times e to the minus lambda, lambda to the k over the k factorial, and that this equals lambda. Sigma squared is equal to the expected value of the quantity, the random variable x minus a to the quantity squared, which through subsequent manipulations eliminates the intermediate variable, the minus 2 lambda eta, and removes that from the expected value, which yields just lambda squared minus eta squared. So that basically comes out to the expected value, where sigma squared is equal to the expected value of x squared, the random variable squared, minus lambda. So we have here the summation, again, of k to the 0 to infinity, the summation of k times lambda to the k over the k factorial, which is equal to lambda times e to the lambda, which implies that the derivative of lambda over the summation from x equals 0 to infinity of k times lambda to the k over the k factorial equals the derivative over lambda of lambda to the e to the lambda, which when broken down gives you e to the lambda plus lambda e to the lambda. That implies, however, that the summation from k equals 0 to infinity of k squared lambda to the k minus 1 over k factorial, which is basically taking the derivative again, equaling the quantity 1 plus lambda times e to the lambda, which implies the summation of k equals 0 to infinity of k squared times e to the minus lambda times lambda squared over the k factorial, which equals the quantity 1 plus lambda times lambda. Sigma squared, which is the variance, is indeed equal to the expected value of the random variable x squared minus lambda squared, which is equal to 1, the quantity 1 plus lambda times lambda minus lambda squared, which is equal to lambda. Indeed, the expected value of the random variable x of t is equal to lambda t, and the expected value of the random variable x squared t is equal to the quantity 1 plus lambda t times lambda t, and sigma x squared t is equal to lambda t. So in essence, what we are saying in effect is that lambda t takes on those roles in numerous places where we have it here, it's lambda, it eventually becomes lambda t. Okay, part B, and this is for the situation where we're using multiple points, where we have t2 greater than t1. The random variable x of t is equal to the random variable x of t1 minus x at 0, or the random variable x of t2 minus x of t1. Looking at the correlation, we have the correlation of t1 comma t2 and the area of independent. We have the expected value of x of t1 times the expected value of the random variable x again at t2, the 2 points there of the random variable. And this is equal to the random variable x of t1 times the variable x of t2 minus the random variable x of t1 plus the random variable x of t1, which is a way of restating the 0, if you will. But this equals the expected value of the random variable x of t1 times the expected value of the random variable x of t2 minus the random variable x at t1. And here's where we apply that separation, and we separate out the plus that the expected value of x squared, the quantity x squared of t1, because we see the difference there. And this is equal to lambda t1 times the quantity lambda t2 minus lambda t1 plus the quantity 1 plus lambda t1 times lambda t2 equal to lambda, the quantity t1 plus lambda t1 t2. And for t1 greater than t2, the correlation of t1 t2 is equal to lambda t2 minus lambda t2 plus lambda t1 t2, which in effect we have substituted and provided an additional function where therefore therefore the correlation R of t1 t2 is equal to lambda times the min t1 t2 plus lambda t1 t2. Thank you very much.